Okay, section 3.7 is implicit differentiation. It's basically taking a non-function and we're going to take its derivative. First one, first of all, you've learned hopefully by now, you got to look and see what you can do first. I'm basically going to show this one in two ways. In this particular case, I'm going to do some algebra first because I can. And if I do that, I want to take a derivative. Why would I do it that way? Why can't I just add x squared to both sides? And now take the derivative with respect to x, giving me dy. The derivative of y with respect to x is 2x. Very simple, straightforward. I used algebra first. But to demonstrate the power of implicit differentiation, I'll show you how to do this without. So I'm going to write down this function as it's written. And this one happens to be a function. It's not written as a function because it's not solved for y. But if I take the derivative with respect to x, watch what happens this time. And basically, we do it over there, you just didn't see it. When I take the derivative of y, I get 1. But I just took the derivative with respect to x. I have to write it. Now, here's the case where I'm taking the derivative of an x. The next term is x squared. I'm taking the derivative of an x. You get 2x. But here I took the derivative of an x with respect to x. That's why we never wrote it. There was never any point. Equals, now be careful, the derivative of 6 is 0. So right now I have dy over dx, subtract 2x equals 0. Or dy over dx equals 2x. So I've done this technique both ways. One is do the algebra first, and second is just to take it as it is and do it implicitly. Next question. Now, if you look at it here, if I attempt to slide over here and do some algebra, forget it. You could try if you'd like to, but not going to happen. So what I'm going to do is I'm going to take the derivative of this as it's written, and I'm going to pay attention to all the details, like there is a product right there. And that's kind of like why I like to rewrite it, because I can see all the pieces here. I see that here this term is just x. It's straightforward. This one I'm going to have to show respect. Now I have an f times a g. G has a y in it. I'm going to have to show respect, which means I'm going to have to write the dy over dx. First one, first term, 3x squared. Second term, I see 3y squared, but there I took a derivative of a y with respect to x. I have to write dy over dx. Equals. Now I'm going to do the product rule. It is a product, hence I've got to do the product rule. So I'm going to write it up here, and I'm going to do it. Derivative of f is 18, no need for respect, times g, just copying g, plus f, just copying f, times the derivative of g. Now derivative is 1, but I have to show respect dy over dx. Now in comes the algebra that's required. So I did the calculus, now I'm going to do derivatives. My job was to find dy over dx by itself. I see two terms have the dy over dx in it. So we're going to get those on one side. The terms that do not have dy over dx in it, I'm going to keep on the right-hand side. So right now, I've got 3y squared dy over dx. Bring over the other one with the dy over x in it, so subtract 18x dy over dx equals 18y, and I'm going to subtract the 3x squared from both sides. Now I've got the dy over dx is on one side. The only way to get these two together is to factor out the dy over dx, so I've got dy over dx, I got one of them. And finally, now that I've got dy over dx by itself, I'm going to divide both sides by that factor 3y squared minus 18x. So I get 18y minus 3x squared over 3y squared minus 18x. Here's the deal. Here's the deal. This is not a function. So if I was to graph it, it could be going all over the place. Who knows? Who cares? All I know is this. This derivative has both x and y in it, meaning in order for me to find a slope of the tangent, I need both an x and a y. The reason is because if I have just x's, for example, like this x here, whatever that x is right there, I could have 3 different locations for that tangent, hence needing the y value to tell me which one of these I'm requiring. So implicit is a way to take non-functions and find their derivatives. Now there's some fun ways to do this, but this next one, but it is just convoluted. It's a hot mess. I see right away I can't solve this for y, so I can't do any algebra. This is straightforward, but then over here I've got a quotient rule. And both the f and the g have a y in it, so I'm going to have to be respectful. Notice here they're giving me a value for which they want the derivative at. I love when they give me numbers. That means I basically I don't have to solve it with the algebra in it. I can solve it with numbers in it a lot easier. So let's roll through this. Derivative of the left side is 2x equals. Now I'm going to do the quotient rule. Derivative of the top, 1 minus, show your respect, times the bottom, minus the top, times the derivative of the bottom. Derivative of the bottom is 1 plus show your respect, all over the bottom squared. Okay, this would be really ugly to try to solve for dy over dx. It'd take about 5-6 steps, and there's a lot of ways to make mistakes. But the beauty of it here is it gave me numbers, which means I could plug in x and y and solve for dyx with numbers in it. So let's evaluate that now. 2 times -1 equals 1 subtract dy over dx times 1 -1 plus 2 minus -1 minus 2, 1 plus dy over dx. Right now I'm just copying and filling in my numbers. And then -1 plus 2 square. A lot nicer to deal with. So I've got -2 equals. That right there is just 1. Distribute the 1, nothing happens. So that's 1 minus dy over dx. Over here, I got -3, but there's a negative outside, so it's +3. So I'm going to distribute 3. All over. -1 plus 2 is 1 square, or just 1. I'm not even going to write it. So -2 equals 2 plus 2 dy over dx. Subtract 2 and divide by 2. Now I know the slope of the tangent at the given point, -1, 2, for something that's completely non-functional. Okay, implicit is not is for non-function, means we may not have a graphic interpretation. That's why I gave the bunch of squigglies. All right, that's it. Please, lots of practice here is necessary. So enjoy. Lots of questions in class.